Hey guys, I'm Jade. Today is my LeetCode review vlog on 104th problem, maximum depth of binary tree. We're given the root of a binary tree. We have to return its maximum depth. A binary tree's maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node. Let's example 1 here to understand it easily. We got an input root node. Node 3, it has 2 leaf nodes. For his left leaf node, the node 9, it doesn't have any further leaf node. And for its right leaf node, node 20, it has its own leaf nodes, the node 15 and node 7. So the maximum depth of this binary tree is 1, 2, 3. It got 3 layers, so the output is 3. Then let's get started with our intuition to solve the problem. And this problem can solve by 2 approaches. The first approach is called recursive depth first search, and the second approach called iterative breadth first search. And we'll solve this problem by the recursive depth first search problem first. So is recursive depth first search. And the detailed step is we'll explore each node and its subtrees recursively and calculate the depth of each subtree. Then we'll take the maximum of this depth. Next, let's get started with a code to solve the problem. Inside the max depth method, the very first step, we have to take care of the edge cases. If root equals null, which means it's an empty node, we just return 0, which means the depth is 0 if the root is null. And for the recursion approach, so we have to recursively calculate the depth of the left subtree and the right subtree. So the code is left depth equals max depth of root dot left. And we also have to calculate recursively the depth of the right subtree. Right depth equals max depth of root dot right. And max depth method, it is also the method here we have to implement. So this is a recursively approach. And at the end, we just return the maximum value between left depth and right depth, and we have to plus 1 to it. This is because the depth of the current node, it is the maximum of the depth of its subtree, the left subtree and the right subtree. And the final thing, we have to plus 1 because we got a root node here. Return math.max of left depth, right depth, and we have to plus 1. Then let's submit code and check the correctness. Yes, our code got accepted. And then we have to analyze the time and space complexity. So the time complexity, it is big O of n, and n stands for the number of nodes in the subtree in this binary tree, because we have traversed each node for only one time. And the space complexity, it is big O of h, and h stands for the height of this binary tree. This is because we use the recursion stack in this problem solution. And there are two cases. In the worst case, such as an unbalanced tree, the height can be n. But in the best case, for example, a balanced tree, the height it is log n. So the height h is between n to log n. And this is the first approach to solve the problem. And we can have another solution. Depth, version 1, public int max depth with version 2. Then let's get into the second solution called iterative breadth first search. Iterative breadth first search. And the detail step is we are going to use a queue to traverse the binary tree level by level, and the maximum depth is determined by the number of levels in this binary tree. Then let's get started with its code and annotations to solve the problem. And the very first step is very similar. If root equals null, we just return 0 to handle those edge cases. And then we have to initialize a queue to hold nodes at each level. And we also have to traverse the tree level by level. Let's say queue of tree node. Let's call it queue equals new linked list. Next, we have to make queue.offer of the root node. We have to put root node into the queue, and then we have to initialize a depth variable starting at 0, and then we'll create a while loop to traverse the queue and the node and the tree and the root node, which means we have to traverse all the nodes in this binary tree. And the code is while queue is not empty, we'll continue this while loop. And inside the while loop, the first step, we have to get the number of nodes at the current level. And the code is int level size equals queue.size. Because when the code runs into this line, we have handled all the nodes in the last level. So we can get the correct queue size, also the number of nodes in this level correctly. And then we have to increment the depth because we started a new iterative check for the new level. And then we have to create a nested for loop to process each node at this level. Int I started at 0 and I should be less than level size and increment I after each iteration. Inside the for loop, first we have to get one node out of the queue. So the code is tree node with current node equals queue dot pull. Next, we'll add the left child to the queue if exists. We have to check if current node dot left is now equal to null. If so, it means the current node has its own left leaf node. So we have to put it into the queue. Queue dot offer of current node dot left. And we also have to add the right left node leaf node to the queue if it exists. If current node dot right is not equal to null, then we have to add it to the queue. Offer current node dot right. And that's all the code inside the for loop. And out of the for loop and the while loop, we just return the depth, and the depth is exactly the maximum depth of this binary tree. Return depth. Then let's submit the code to check for the correctness again and analyze the time and space complexity. Yes, our code got accepted. So the time complexity, it is also big O of n, and n stands for the number of nodes in this binary tree. And the reason is also similar, as we also traverse each node in the binary tree for only one time. And the space complexity is kind of different. It is big O of n. This is because we create a queue to hold all the nodes at each level. And in the worst case, the queue we created can hold up to half of the nodes at the last level. And for this case, it is big O of n. And this is the end of my LeetCode review vlog on this problem with two different approaches. And I highly recommend you guys to visit my online GitHub page here, which contains all the nodes for top 150 LeetCode problems. And for each problem, you can see very detailed problem description, intuition, Java code, annotations, and the final time and space complexity analysis. You can also visit my GitHub repository here, which contains the code and nodes to build this online GitHub page. And I'll put those two links on my YouTube description below. And thank you guys for watching. I'll see you next time. Bye bye.